Modern electronics are built on a fundamental tension. We have delicate microprocessors that operate on tiny fractions of a volt, sitting right next to massive industrial motors that require these huge, destructive surges of electrical current to function. If you were to wire that delicate silicon chip directly to a heavy-duty motor, the sheer force of the power draw would instantly incinerate the sensitive processor. In 1948, engineers developed a physical solution to this exact problem, the Bipolar Junction Transistor, or BJT. A BJT is a three-terminal semiconductor device designed to let a tiny electrical current control a much larger one. This single microscopic component acts as an electrical gatekeeper. It safely bridges the gap, allowing delicate computational logic to direct raw mechanical power without ever being crushed by it. This diagram shows the anatomy of a BJT, which is built as a three-layer semiconductor sandwich. You have the heavily doped emitter, which acts as the source of electrical charge. In the middle sits the ultra-thin, lightly doped base, acting as a control gate. On the side is the collector, which receives the charge. Looking at the schematic, transistors come in two varieties, NPN and PNP, depending on how the materials are stacked. These layouts translate into standard symbols. The emitter arrow points outward for NPN and inward for PNP, indicating the direction of current flow. Regardless of how those specific positive and negative materials are stacked, this exact three-layer physical anatomy is what allows a tiny electrical input at the base to dictate a massive electrical output across the entire component. Let's track a faint electrical signal as it travels down a wire and enters the base terminal. It hits the forward-biased base-emitter junction, which is the physical boundary between the first two layers. Because the base layer is incredibly thin and holds very few charge carriers, this tiny input triggers a massive cascade effect. It pulls a violent rush of particles up from the heavily doped emitter layer. That heavy surge of particles sweeps straight through the thin base. Its momentum carries it right across the reverse bias junction and directly into the collector layer. The base acts exactly like a highly sensitive physical valve. By applying just a whisper of current to the center layer, you unleash and regulate a heavy torrent of electricity flowing from the top of the device to the bottom. Having three distinct terminals gives circuit designers incredible flexibility. They can wire the exact same physical transistor into a circuit using three completely different configurations. The most widely used setup is the common emitter configuration. Engineers route the signal this way when they specifically need massive current and voltage gain to drive a much larger load. There are also the common collector and common base configurations. These are used for specialized routing, like buffering delicate signals or managing high-frequency radio waves. By simply changing which of the three terminals is shared across the circuit, engineers transform the BJT from a brute force power amplifier into a precise high-frequency signal router. But what happens to that microscopic control valve if the tiny input signal traveling down the wire is replaced by a beam of light? You get a phototransistor. In a phototransistor, the base terminal is physically exposed to incoming photons. It converts the intensity of that light directly into the base current needed to trigger the transistor. This brings us to the optocoupler. An optocoupler is a single sealed dark chip that traps an LED light source and a phototransistor together inside. The LED fires a beam of light across a physical empty gap to strike the base of the phototransistor. The mechanical advantage of this setup is perfect electrical isolation. You can control high-voltage systems using light across a physical gap, meaning there is zero direct wiring between the input and the output. In the real world, this isolation protects sensitive medical monitoring equipment from deadly electrical surges. Bridging the circuit gap with a photon rather than a wire ensures that a catastrophic high-power electrical spike can never physically travel backward to destroy delicate, life-saving logic boards. The way a BJT behaves depends entirely on how hard it is pushed. When resting in its active region, the component acts as a proportional analog amplifier. In this state, it takes faint, imperceptible audio signals and smoothly boosts them, so they can broadcast out of radio transmitters or drive massive loudspeakers. But you can push the transistor past that smooth middle ground to its absolute limits. The BJT is the ultimate region of the technological age. It harnesses the invisible physics of subatomic particles, so that a whisper of electricity or a single flash of light can seamlessly command the raw mechanical power of the modern world.